In this video, we are going to discuss force current analogy to convert mechanical translation system into electrical system. In last class, we observed force voltage analogy to convert any mechanical translation system into electrical system. So in this class, we will study force current analogy for converting mechanical translational system into electrical system. So now we see the conversion step. Okay. In mechanical system, the input and output are force and velocity. And in electrical system, input is current source and output is voltage across that element. And we know in mechanical system there have three elements. One is mass, second one is spring, and third one is damper. Okay, so see how we will analyze these three elements of mechanical system in electrical system. Okay, so see force of mechanical system is analogous. So see first, force of mechanical system is analogous to injected current in electrical system, and velocity of mechanical system is analogous to voltage of electrical system. Next, if we are having mass m in mechanical system, then this mass can be treated as capacitance C in electrical system. Next come to the viscous friction coefficient B. So if we are having viscous friction coefficient in mechanical system, then this viscous friction coefficient can be treated as reciprocal of resistance in electrical system. This reciprocal of resistance sometimes called conductance also. Okay. And last one is, if we are having stiffness constant, that is spring constant in mechanical system, then this spring constant can be treated as reciprocal of inductance in electrical system. Okay. So this table represent how we will convert any mechanical element into electrical element according to force current analogy. Okay. Now see the rule or step which have related to conversion of mechanical system into electrical system according to force voltage analogy. So see here I have mentioned four important point which have related to conversion of mechanical translational system into electrical system based on force current analogy. Okay, so first point is first step is in mechanical system, the elements in parallel will show same force. In mechanical system, the elements in parallel will have same force. Okay. So take an example. See, in mechanical system, if we are having two or three elements in parallel, then the all elements will show same force. Will get the same force. Okay. And here similarly in electrical system, parallel elements will have same voltage. So that is general matter. So any electrical network, parallel elements will have same voltage similar to the mechanical system. Parallel elements will get the same force. Okay. So this is our first point. So first point is, in mechanical system, the elements in parallel will have same force. Similarly, in electrical system, parallel elements will have same voltage. Okay. Now come to the second point. Okay. So here in second point, each node in mechanical system, node means mass or meeting point. So each node or mass or meeting point in mechanical system correspond to a node in electrical system. Okay, node in mechanical will be treated as node in electrical. So now come to the third point. Third point is number of node in electrical system is equivalent to number of node in mechanical system. So that means number of mass element in mechanical system will give you the information about the number of nodes in electrical system. Clear? Now come to the last point. Okay, so in last point, if the elements connected between two nodes in mechanical system is represented as common elements between nodes of electrical system, so what about the elements we are having in between the nodes of mechanical system, the same elements or the analogous elements in electrical system? We need to consider as common element in between the nodes of electrical also. Okay, so fourth point is, so what is the fourth point? Fourth point is the elements connected between two nodes in mechanical system is represented as common elements between nodes of electrical system. So what about the elements we are having in between the nodes of mechanical system? The same elements or the analogous elements in electrical system we need to consider as common elements in between the nodes of electrical also. Clear? So this is our last point. So see, by taking the reference of that table, force current analogy table, which I have discussed previous slide. So by taking the reference of that table and these 4 points, I want to convert one mechanical system into electrical system by using force current analogy. Okay, so now I will take same example which I have also taken in force voltage analogy. Okay, so you understand, you people have understand what is the actual difference between the circuit according to force voltage analogy and according to force current analogy. That's why I have taken same example. Okay, so see the example. So see, in force current analogy, nodes are important. So how many nodes we are having in the electrical system? That means how many nodes we'll have in the analogous electrical system for this mechanical system which I have mentioned in this example. Okay, so how many number of nodes in electrical system is that can be described by the mass element. The number of nodes or mass element in mechanical system will describe the nodes in electrical system. So here we are having two masses M1 and M2. So we may have two nodes in electrical system. Okay, and here I am considering these two nodes is V1 and V2. Okay, and each node is having some voltage. Okay, and so that voltage I am considering V1 and V2. Okay, and now we need to consider each element of this mechanical system. Okay, so here we are having first is force. So force in mechanical system is equivalent to current source in electrical system. Okay, so I am taking a current source connected to V1 node. See the electrical circuit. Okay, that means V1 node, that's why I am connecting a current source with the V1 node. Okay, next element is mass element M1. So M1 itself is meaning of capacitance. So for the same node, a capacitance C1 is also attached, which I have given in the electrical system. See the electrical system. And here for same node, another friction coefficient B is there, and this B is only related to this mass M1. Okay, so when we see friction coefficient, we need to take resistance. Okay, so for same node, resistance R is connected to same node, means V1. Okay, now coming to the spring constant K1 and viscous friction coefficient B1. Okay, so now coming to spring constant K1 and viscous friction coefficient B1. Okay, and these two elements are these two elements, that means B1 and K1, are the common elements between mass M1 and mass M2. So that means these two elements are in between nodes of two mass element or between the nodes. So in electrical system, we need to consider these elements as common element. Okay, so here we are having spring. First we are taking spring. Okay, so for spring we need to consider inductor. Okay, and second we consider dashpot or viscous friction coefficient. So for this dashpot or viscous friction coefficient, we need to consider resistance. Okay, so these two element I consider as common element between two nodes. Okay, so see here I am giving the name of inductor, which is analogous to see here I am giving the name inductor L1, which is analogous to K1, and the name of the resistance is R1, which is analogous to viscous friction coefficient B1. Okay, now come to the second mass, that means M2. Okay, so M2 is itself represented with a capacitance. Okay, so I can take a capacitance and give name C2 because this is related to M2. And after that M2, we are having two elements only related to this mass M2. So these two elements only related to node V2. Okay, so here spring K2. So spring means again here consider inductance L2, and here also we are having dashpot, that means viscous friction coefficient. So we need to consider resistance naming by R2 because this is related to B2. B2 means viscous friction coefficient B2. Okay, so this is the total electrical network related to this mechanical system according to force current analogy. Okay, so see here in force voltage analogy we take in series, where in force current analogy we take in parallel. So you can see all the elements are in parallel with same voltage. Okay.